Okay, so we continue the lesson we started last time, namely the derivative and properties of curves. If you remember last time, we reached to the point that we want to find the inflection points of some curves or functions. So do you remember? So this is one scenario that I was talking about. For example, this point approximately. This is an inflection point for this curve, yes? Why is that? Because if I draw this border, before this point, the function is concave down, and immediately in passage of that point, the function becomes concave up. So this type of function is this type of point for a function is called an inflection point for the curve. Yes, of course I can have the other scenario, so I might have this way, that's also possible. But yet, the last time I tried to convince you, and hopefully I succeeded, to show that if the function is concave down, the second derivative plays a role here. So let me just review this. So if I ask you, if this is the function y equals to f of x, yes, and I give you this point, so let me draw the coordinate system, for example. So if this point is A, I want to ask you about the sign, positiveness or negativeness of f prime of A and f double prime of A. So I want you to understand these two numbers from geometrical point of view. So hopefully you can immediately answer me if f prime of A in this particular picture positive or negative. So how do I understand that? I draw a tangent line at this point and then see if the slope is positive or negative. So in this case, the slope is positive. Yeah? So this means that for this particular picture and for this particular point, I know that f prime of A is positive. So this is important to be able to immediately understand at which point on the curve the function, the derivative is positive, and at which point it is negative. It is very simple. You just imagine in your head the tangent line and see if it is positive, if it has a positive slope or a negative slope. And of course, if it is horizontal, the derivative becomes 0. But what about in this situation, if I ask you what is f double prime of A, positive or negative? So, when it comes to the second derivative, then the notion of tangent is, of course it is important, but not as important as for the first derivative. You need to think about concavity of the function, yes? So if you consider this point, in the vicinity of that point, in the neighborhood of that point, the curve lies below the tangent line, okay? If this happens, it means that the curve at that point is concave down. So because if you have an upside down ball, it doesn't matter where you draw the tangent, the curve is always below those tangent lines. And if it is concave up, it doesn't matter where do you draw the tangent, the curve is always above the tangent lines. So that is the idea. So here, for example, you see that what happens? This curve in the neighborhood of this point, for example, say between these two very close points, this part of the curve is always below this tangent line, so this means that the function at that point is concave down. So for this particular function, this is definitely the case that f double prime is negative. Yes? So that is the way that you realize when f prime is positive or negative. Okay, and then of course, for the inflection point, I have a little bit of problem, yes? So for example, if I ask if this is point C, and I want to ask the same question, f prime of C, what is this one? Is positive or negative in this picture? So I draw a tangent line. If you have inflection point, this is what is happening. If you draw the tangent line, Yes, I cannot draw it perfectly fine, but this is what happens. I mean, at some point, the curve is below the tangent line. At some other point immediately, the curve is above the tangent line. So something like this happens, yes? So for example, if this is the inflection, this is an inflection point. I cannot draw it perfectly fine. So it's better to draw this one first. Something like this, yes? So that is an inflection point. This is an inflection point. Of course, this is an inflection point opposite to this one. This one first. If you see this point, before this point, the curve is above the tangent line. But immediately after that point, the curve is below the tangent line. So we say that the tangent line actually passes through the curve itself. Okay, so but in this case, in this picture, if I ask you f prime of c is positive or negative, you see that the tangent line has negative slope, so definitely this is the case. But if I ask you what is f double prime at c, this is 0. So we can say that the second derivative at the inflection point is 0. Yes? Okay, but now, of course, this is the question. A function is given to you and you are supposed to find the inflection points. I did 2 examples last time, but let me start with that example, another type of this example again. So let me just write it very simple. Okay, so I give you a function, f of x. You do not have access to the graph of the function. The function is x to the power of 4 minus 4x cubed plus we have 5. Okay? About finding extreme points and terrace points we learned. That was the name for a theorem called the first derivative test. But now today I want to talk about inflection points. If there is any inflection point. Or inflection point or points. I don't know how many of them are. So this is something I want you to remember. What should I do as a recipe if I want to do it algorithmically? You realize that the inflection point has something to do with the second derivative. Yes? The point at which before that the graph is concave down, meaning the second derivative is negative, suddenly the second derivative becomes positive, is an inflection point. The other way around is also an inflection point. Before that point, it is concave up, so the second derivative is positive. After that, the second derivative is negative. So the important thing is that the second derivative at the inflection point should be 0, but that is not enough because might be this is not the case. You have to check if the second derivative sign is really changing. This is important. So what you do for finding an inflection point, you need to know the second derivative. In order to know the second derivative, the first step, of course, is to know the first derivative, which becomes what? Minus 12x squared. And then the second step is to take another derivative. So whenever you see the inflection point, you need to realize that it is related to the second derivative. If I take another time, so it becomes 12x squared minus 24x. Okay? Now the third step is to equate the second derivative to 0 and solve it. Okay? Okay, this is a quadratic equation. It is easier here in this case to factorize it. We can do it faster. If I factor 12x out, then it becomes x minus 2 equals to 0. And then what can I conclude? I can conclude that either x is 0 or x is 2. So one common mistake among students is that they jump immediately into this conclusion that there are 2 inflection points. But I want to warn you about that. Some of them might not be the inflection point. This tells you that if there is an inflection point, it should happen either here or there or at both. But it doesn't guarantee that these are inflection points. You have to test if they are inflection points or not. But before, this is, by the way, what I want you to tell, potentially you have infinitely many choices in front of you for a function, for inflection point of a function. But now we narrowed it down to only 2 options. But still there is no guarantee. What I can write, I can say that these are candidates for inflection points. Yes? So this I want to emphasize here. But how should I know that if they are real or not? So you need to see if the second derivative is changing sign at those points or not. So you draw some table which is similar to the sign table, but you have 3 other rows. The middle row, instead of being f prime, is f double prime. And the third row is, as usual, f. And then you put these numbers 0 and 2 here. Okay? When x is equal to 0 or 2, the second derivative is 0. So this means that the second derivative is 0 here. And if I put 0 in the function f itself, I get 5. And if I put 2 in the function itself, so what happens? This becomes 16. This becomes 32 minus 16 minus 11. That's minus 11. Yes? And then you need to know where the second derivative is positive and where the second derivative is negative. So where is your second derivative? Your second derivative is this guy. And then you can use the same recipe for the same reason. So if you want to see if double prime is positive or negative, you choose a random number smaller than 0 here. For example, the simplest possible one is probably minus 1. And put minus 1 here. You get a positive number because this becomes 12, this becomes plus 24, it becomes positive. And I told you because of those things that we described previous time, it remains positive all the time. Between 0 and 2, a random number, the best choice is probably 1. And I put it back here, 12 minus 24 is minus 12, which is negative. And then after 2, for example, 3, this becomes 9 times 12, definitely is bigger than 24 times 3. So this is positive. Okay, but do not put these arrows. These arrows, we don't know, by the way, because this is the sign of the second derivative. If you want to draw something, if f double prime is positive, it means that the graph is concave up. If you want to do a symbol like it is, you can just do it like this. And then here, the second derivative is negative, so it is concave down. And here, the second derivative is positive, so it is concave up. So are these candidates real inflection points? The answer is yes. Because you see, at the point 0 and 5, before 0 and 5, the function was actually concave up, and immediately after that, the function becomes concave down. So yes, this is an inflection point, and for the same reason, the point 2 and minus 11 is also an inflection point. Yes? So these two are inflection points on the graph. Yes? Is that clear? Okay, but I want to warn you, this was the case that both of them were actually inflection points. So if you just here stop the problem and say that I have two inflection points. Coincidentally, you did the correct one. So because that was really true. But this is not always the case. For example, let me repeat this example from last time. So if I ask you about this function, I want to show you that if you are careless about my emphasis here on candidates, you will get an inflection point for this function. Okay? So let us just do the same thing, but don't go here and stop there. You see that you will get a conclusion which is wrong. Let us check. The first step, you take the first derivative. It becomes 4x to the power of 3. The second one, you take the second derivative. It becomes 12x to the power of 2. And then the next step, you equate the second derivative to 0. What do you get? 12x squared is 0. What do you get? You get x is equal to 0. If you stop here and say that this is my inflection point, this is the wrong conclusion. Why is that? Because if you draw this table, you have x, f double prime, and f. X is 0. The derivative is 0. The second derivative is 0. And here, coincidentally, the function is also 0, because if I put 0 here, you get 0. Okay, but now I want to see if this is positive or negative or whatever it is. I choose a random number smaller than 0, say -1. I put it in the second derivative. But when I put -1 here, because of this even power, it becomes positive. And when I go and choose a random number greater than 0, for example 1, and I put it here, again it becomes positive. So what happens, it means before this point, it is concave up. After that point is again concave up. So what does it mean? It means that this is a fake one. It's not an inflection point, yes? So, therefore, this function does not have any inflection points. Yes? And if you really ask Geogebra to draw the graph for you, this is very similar to a quadratic equation x squared, but it is steeper. So I mean, for example, yeah, you will see something sharper going up. This is the graph of x to the power of 4. And it is clear that this point is not an inflection point. By the way, what type of point is that? Yes? Yes? It's a minimum. So this is what I want to say, that if you just take the second derivative and put it equal to 0 and take it for granted that this is the inflection point, it might not be true, as this very simple example shows. Okay, so when you take the second derivative and equate it to 0, you might get a bunch of numbers or a bunch of points, but these are just candidates for the possible inflection points. To confirm that if they are true or false, you have to draw this. I don't know there is a name for this table, or even I don't see it in your book, but anyway, you have to design, you need to know the sign of the second derivative. If the sign of the second derivative changes in passing through that point, that candidate is a real inflection point. If not, that's just a fake one. It's not an inflection point. Is that clear? Okay, so this is important to understand. Because drawing the graph of functions is also part of your education here in Math 4. Actually, this is the reason. So let us try to draw the graph of this function. But draw probably is not a good word. I have to say sketch, because we want to highlight the salient points on the graph, not precisely. If you want to do it precisely, of course, you can use a computer to do it. Okay, let us try. I'm changing the topic a little bit. This is more or less the previous lesson. So I give you the same function, x to the power of 4 minus 4x to the power of 3 plus 5, and I ask you sketch the graph. Okay, if I ask you to sketch the graph, oh, by the way, this is recording very badly. Okay. So how should I do that? If you want to sketch the graph, the first thing you need to know is to find the max and mean. Okay, so the first thing you do is to take the derivative of the function. Of course, to be honest, the first thing you do, you need to know the domain of your function. What is the domain of this function? There is no limitation for the values of x that I can put in, so the domain is the whole real number. There is no special point that I have to get. Most of the time, this is the case for your problems. Number two, I take the derivative. The goal for taking the derivative is I want to find the extreme points, local extreme points, using the first derivative test. So let me just take it 2 steps. I take the derivative first. It becomes 4x to the power of 3 minus 12x squared. And then the second thing that I do, I take it and put it equal to 0 and solve it. So this becomes 4x to the power of 2, 3 minus 2, 12x squared. I equate it to 0 to see what happens. So to solve this equation, it's a third degree polynomial, but it is easy to factorize it. So I take 4x out, or 4x squared I can take out. Then from here, there is only 1x left, and from here, 3 is left. Yes, and then if I solve that equation, it becomes either x is equal to 0 or x is equal to 3. At this point, if I ask you, what are these? What is your answer? Yes?
Candidates.
Candidates were?
Heading.
No, inflection comes with the second derivative.
Oh, extreme.
Extreme points or terrace points, which is a particular case of inflection points, yes? So these are candidates only for extreme, local extreme points or terrace points, but still we don't know which one is which, if any, okay? So to understand that, I need to use the first derivative test. So first derivative test means the sign table. So I have the sign table x, the middle row is f prime, don't get confused, that was the inflection point, and this is f. These numbers that I got, I put them in order from left to right. And then what is f prime at these 2 points? Exactly 0. Because I myself put the derivative equal, oh sorry, I made a mistake here. This is not double prime, so might be this is why you are confused. But this is just f prime. I don't know why I put f double prime. Okay, and then I need to calculate these numbers. For these 2 numbers, I need to refer to the original function f. So I take 0 and put it in my original function. The answer becomes 5. I put 3 and put it in this original function. So what is the answer? 3 to power 4 is 81. 3 to power 3 times 4 is minus 108. And then I have a 5 here. So it becomes minus 22. Yes? Am I right? Minus. Yes, it is correct. Okay, and then what I do, I need to see if this is positive, negative, or positive. So what is the idea? The idea is go and find a random point, for example, minus 1, but don't get confused because this row is f prime row. So you need to go and look at f prime. If I put minus 1 here, this becomes negative, negative, so it becomes negative. Yes? Now, if between 0 and 3, I put, for example, what? I put 2. This becomes negative again. Do you agree? And if I put 3, after 3, for example, 4, then it becomes positive. It's not that hard to convince yourself this is positive. So then here, the first derivative is negative, so the function goes down. Here again, the function goes down, it's decreasing, and then immediately after that, the function is increasing. So actually, yes, one of them was not a local extreme point, yes? So this point is, what type of point is this point? 0 and 5, it is a terrace point, yes? So 0 and 5, a terrace point. What type of terrace point is that? It is decreasing type. So the terrace point is something like this here. But 3 and minus 22 is what? It goes down and then goes up. Okay, so what happens? That's a minimum, yes? A local minimum. Or the local minimum. In this case, there is only one of them, yes? Yes? You see that when I want to sketch this graph, I haven't done that part yet. But of course, for this particular function in the previous example, I also found 2 inflection points. To be very precise, you need to also include that one. But according to your book, you don't need to do that much. Okay, so what we do, sorry. So what you have to, if you want to sketch the graph, first of all, you know that there is no there is no limitation for the domain. So it goes from minus infinity to infinity. And to respect that, it is usually common to write this domain here. Yes, I do not have any limitation. So every value from minus infinity up to plus infinity is acceptable. Okay. So now let us find these 2 points. So I have to be a little bit out of scale. So 0 and 5. So assume that the x coordinate is 0 and the y coordinate is, say, 5. So this point is what type of point? Is a terrace point. Yes? So what type of terrace point? This type of terrace point. So it means that so yeah, this you guide yourself like something like this. You guide yourself to draw it. Make it better a little bit. So let us keep it like this. So we don't know exactly how, but we know that in the neighborhood of this point, the graph looks like that. And then I have 3 and minus 22. So say, for example, here is 3. So let me keep this one 3, it's larger than 5, so scalings are not the same. And then minus 25, minus 22 is more or less 4 times this down there. So assume that here is minus 22. And then what the graph looks like here, it's a local minimum point. So you can draw this for your guidance, yes? So these are the how graph looks like at these points. And then one thing is important, there are no such, and you don't expect any other surprises here, because if there are, you were able to detect it here. So this means that this is very good. So then hopefully you realize what is going on. So these 2 should be connected, okay? And then this will continue. And then I do not have any kind of surprises after 3. So it means that it should continue forever like this. I will not expect that this will return at some point, because if it starts returning back, there should be another point whose derivative is 0. But I already put the derivative to 0 and I only got 2 answers. So this will never come back anymore. So this will continue forever. And the same thing here for this one. This is a sketching of the graph. Why, for example, you might say that, is there any way for me to understand these exact points? Of course, if you can find them, your graph look more precise. But that is not that important for your case. I don't expect you to miss this bend here. So if you draw it like this, then I will actually deduct some point from you, because now here you have a bend. If you don't see it, it means that you don't understand it quite well. So we need to see this, okay? But except for that, that's enough. So you see that this is a very strong tool. By the way, this is a mathematical way to understand that the graph looks like this definitely, and it will not have any other surprises for you. So even if this is your screen, in your monitor here, you don't need to look to the right that much or to the left. Yes, because you know that this graph will cut. This is the essence of this graph. Yes. So this is somehow a sketching. But if you want to see where are those points, by the way, 0 and 5 is already this point. Did you expect to get that? At that point might not, so we might not expect to get that, but we know that 0 and 5 is an inflection point. But according to this calculation, we realize that inflection point is actually a terrace point, because that's 0 and 5. So every terrace point is an inflection point. So let me write it for you. Every terrace point is indeed an inflection point. But not the other way around, yes? Yes, so this is something it's good to know. So that is expectable. So here I couldn't guess that is a terrace point. But now I realize that inflection point is really a terrace point. But there is another one which is 2 and minus 11. Do you think that is also a terrace point? Because we know that 0 and 5 is an inflection point. We know that 2 and minus 11 is an inflection point. Based only on this calculation, I couldn't foresee that 0 and 5 is also a terrace point. Yes? But now by putting the first derivative equal to 0 and getting the same point, I realize that that particular inflection point is a terrace point. Now my question is that, do you think that this might be the case for this one as well, that 2 and minus 11, which is already an inflection point, is also a terrace point? Do you think this is possible?
I think no, because then we would have gotten it.
Exactly. Because if this is going to be what? If this is going to be a terrace point, it means that when I put the derivative equal to 0, I should also get 2. But I didn't. So this is a real, so if you want to say real, it is a real inflection point. By the way, where is that inflection point? Can you see it from this graph? So now it shows me something. It shows me qualitatively, probably I made a mistake here. Yes? Because, for example, is that right? So might be 2, I don't know where this is. Okay, 2 might be here. Is it here or there? Because, by the way, how can I answer these question marks if I want to do that? I want to show you that this is not easy to answer. How can I find the exact value of these question marks? Yes?
Y is 0.
Yes. If I put y equal to 0, then I have to solve this hard equation that I don't know how to solve. Yes. But what do you think? Do you think that 2 is below this one or after that one? That is also interesting because 2 and minus 11, I would expect that this should be around here. So then it means that I didn't do a good job because, of course, it is good, but I mean, this should come here, up to here, and then probably, so I mean, it is very hard for me to draw it perfectly. So it should look like this, okay? So this is also an inflection point, which I don't see it properly. So it is good idea to see it using GeoGebra to see how it looks like. But our prediction is that 2 and minus 11 is actually another inflection point. So we should see this kind of property, yes, around at that point. Let us check it using GeoGebra. 4x to the power of 3 and then plus 5. So plus 5. Yeah, so we more or less did a good job here. So that's very similar qualitatively to my picture. But of course, I have to rescale it so that you can see. Usually I should be able to rescale it. I don't know why it doesn't work. This GeoGebra is a little bit... It doesn't work, but... Okay, so let me do it. Oops, I did it the wrong way. 1 to 5. So something like this. Okay. So if I want to zoom out, that you can see. So it is very similar to what I did. But still, the curve is so, I mean, small, so we still don't feel that this should be an inflection point, yes? So let us, by the way, choose that point. What was the point we predicted? 2 and minus 11. So I would say A is equal, let me inflection point, let us show it with I, and 2 and minus 11. Yes, so that is the point. Okay, so this is another, so I mean, it is not that easy to see, but there is one way to confirm that. Can you tell me how? I mean, it's at this point, it seems like a straight line. It is very hard to see on the left what is happening, on the right to see what's happening. Either I can rescale it again to see this, or let me just draw a tangent line. So where is the tangent line? The tangent here. So I click on this curve and that one. What do you expect? No, a straight line, but how? It should be like if our prediction about this is correct, you should expect that the tangent line passes through the graph. One part should be on one side, one part should be on the other side, if that is an inflection point, yes? So now if I press here, that is happening. But it was not that easy to see. So you see, this is what really an inflection point, which is not a terrace point. So you see that exactly in the passage of this blue point, on the left-hand side, the graph is concave down, and then immediately after that, the graph becomes concave up. Okay? So you see that every property that we predict using this derivative is actually happening. Might be another ways to rescale it a little bit more so that you can see that. Yeah, it is a little bit better. So let me rescale that even 1 to 20. Now it is more or less clear that this is really an inflection point, which you were not able probably to detect in other scales. Yes, is that clear? That's an inflection point. Yes? So this is actually the behavior of your graph finally. So if you rescale it and engineer it a little bit, then this graph looks like that. So this is, I want you to understand, this is not possible without mathematics. So how do you know that this kind of behavior you should detect from this graph? But here, using the derivative, we can do that. Okay, any questions? Okay, so this is also something about sketching the graphs. Now let us actually there is another test. I think you have studied that in Math 2C. Do you remember what I want to talk about? There were two tests. So here I called it the first derivative test because there is another test which is called the second derivative test. Not for the inflection point. For the inflection point, we have one algorithm, and that is the algorithm that I described here. But for finding local extreme points, only local extreme points, not terrace points, we have two alternatives. One alternative is the first derivative test, which we described and learned, hopefully. And there's one more, which is called the second derivative test that I want to explain now. But unfortunately, it is not as strong as the first derivative test. Sometimes it remains silent. It cannot answer any question regarding the local extreme ones. Okay, but I want you to again understand the problem because these algorithms are very close to each other. You might get confused. Okay, now my question for you, because if you can answer this question by thinking yourself, probably in the exam, if you have forgotten, you can think and remind it to yourself. So how do you think, using the second derivative, I can find local maximum and local minimum? If I ask you, how can I use the second derivative to find the inflection points, hopefully you learned here. But now I want to use the second derivative test, not for locating the inflection points, for locating the old points that we learned before, namely local maximum and local minimum. But I want you not to use your memory. I want you to tell me why do you expect that, yes? No, we did that. That was the first derivative test, I did it. But here you see, I located the terrace point and local minimum point only using the first derivative. Now my question is that if I want to detect the local extreme points, not terrace points, this will not work for terrace points. It sometimes works for extreme points, minimum or maximum. How can I use the second derivative to detect a local extreme point? Yes?
I mean, it talks about concavity, so we can see that at maximum point, that the second derivative is decreasing because of the concavity.
No, the second derivative is negative because, yes, you are right. Because whenever I have a maximum point, so here, this is a maximum point. Let me call this one point A. Here. This is a local maximum, yes? If I ask you what is f prime of A, what is your answer? F prime of A. What's the answer? 0. Because this is 0. But if I ask you what is the second derivative at A, you cannot say me the exact value, but you can tell me if it is positive or negative. Which one is this? Yes? It's negative because at the maximum it is concave down. So this is negative. And for the case of a local minimum, what do I have? For example, say this is B. If I ask you what is f prime of B, so this is local minimum. If I ask you what is f prime of B, what's the answer? 0 again, because the tangent line is horizontal. But what is f prime of B, positive or negative?
Positive.
Positive. So you see, you discovered it yourself. If you understand the meaning of the second derivative and first derivative geometrically, this is the only thing that you need to remember. The rest of it, if you forget, in principle, you should be able to get it back. So this is local minimum, and that is local maximum. So what is the recipe? The recipe is that for you, this is called the second derivative test. So the second derivative test so again, let me emphasize, for local extreme points, so let me emphasize, not terrace points. So if you really want to find the terrace point, forget about this test, because this will not provide you with any of those terrace points. So what should we do? The first thing is that we calculate the derivative, yes? Number two, we calculate if we solve this equation, and then, for example, I go and get some points. For example, I solve this equation and I get point A, for example. The third thing that I do, I calculate the second derivative. And the fourth one that I do is this conclusion. I calculate f double prime of that number I got. Yes? After doing that, there are three scenarios. F prime of A is 0. F double prime of A is positive. It means minimum. F prime of A is 0. F double prime of A is negative. Then it is maximum. So let me just emphasize, local minimum, local maximum. And unfortunately, there are some cases that not only the first derivative is 0, the second derivative at that point also turns out to be 0. Then it means that you have wasted your time completely, because this is not answering your question. So I would say that the test is not inclusive. or it might be the test is silent. It cannot give you any answer here. So it means that if you are unfortunate, after doing all these calculations, you realize that not only the first derivative is 0, the second derivative is 0, more or less you have wasted all the calculations, you have to go back, and then only do it using the first derivative test. So the first derivative test is stronger, I will come to you, from two perspectives. First of all, it always answers your question about the local extreme points. Furthermore, it will also answer about terrace points. So from the beginning, there is no hope for this test to be answered any question about the terrace point, but even worse, if it is also this case, it cannot answer the local extreme points either. Yes?
If both the second derivative and the first derivative is 0, what kind of point is it?
Everything.
Okay.
I can give you an example. So that's why it's silent, you know. Every possibility can happen. And then let me, yeah, that's a good question. Let me just try to convince you. So you see, I will give you three functions, but very quickly. One function f of x, x to the 4. And then another function g of x minus x to the 4. And then another function h of x, x to the power of 3. Okay, and then I will concentrate on the point 0. Yes? Okay, just let us do the calculation. So what is f prime x here? This is 4x to the power of 3. What is f double prime of x here? It is 12x squared. So here, if I ask you what is f prime 0, what is f double prime of 0? This is 0. Yes? Let me do the same calculation here. So g prime of x is what? Minus 4x cubed. G double prime of x is minus 12x squared. If I ask you calculate g prime of 0, if I ask you calculate g prime of double prime of 0, you get 0. Yes? And then let me calculate this one. H prime of x is 3x squared, and then h double prime of x is 6x. And then if I ask you h prime of 0, h double prime of 0, hopefully you agree again, both of them are 0. So you see that I gave you three functions. I calculated the first derivative and the second derivative for each one of them and calculated those at the same point 0. All of them are 0. But now, you can draw it using Geogebra, but you just trust me on that. So if you draw the graph of this function, it is very similar to a parabola. But this point is what? A local minimum. So for this case, we get a minimum point. Yes? But if you draw this graph looks like this. Yes? And then again, the condition is the same as before, but this time this is what? Local maximum. And now if you draw this function looks like this. Yes? Again, the same condition is happening here, but this one is a terrace point. Yes? So, when this condition that I told you is silent, the test is silent, happens, you don't know anything. It might happen that this is a local minimum or a local maximum or a terrace point. So this is why that test is really silent. Yes? So you cannot, so I would say that in that case you have wasted your time here. So if you really want to know about the nature for this point, if this happens, you have to go back and use the first derivative test. Is that clear? Okay. Simple example. Let me give you a simple example here so that you can do it using the second derivative test. So let me write this. X to the power of 3 minus 2x squared plus x minus 1. Okay, we want to use the second derivative test, if possible, to locate all extreme points or local extreme points for this function. Use the second derivative test Of course, whenever I say this, I always mean if possible, because you'll realize that sometimes it is not possible. Use the second derivative test to locate, to determine the local extreme points and specify the nature of them. Yes? By the way, if the question in the exam comes and they specify you a given test, you have to follow that, even if you solve it with the other test and it is completely okay. Yes? So here, if I want to solve that problem using the second derivative test, you need to know, this is the algorithm. You calculate the derivative, the first derivative, equate it to 0, find the answers, calculate the second derivative and plug these numbers here and follow this recipe, yes? So let us just do that. First, I calculate the first derivative, which is 3x squared minus 4x plus 1. Then I equate it to 0. And I equate it to 0 and solve it. Okay, this is a quadratic equation, so I don't waste the time, so I can do it in my head. So one answer is 1, it's very clear, and the answer is 1, the other one is 1/3. I skipped that part, that is easy, you can just use PQ formula or ABC formula. But now I need to calculate the second derivative. So the second derivative is now 6x minus 4. And now you see, if it works, it is simpler than the first derivative test. You don't need to draw that table and things like that. You just calculate the second derivative, and then you plug these numbers here. So what I do, I calculate f double prime of 1. So it becomes 6 minus 4, which is positive. So this means that this is really an extreme point. What type of that? The first derivative is 0, the second derivative is positive. So this is this case. So it's a local minimum. So this means that 1 and f of 1. F of 1 is, by the way, here is simple, yes? So it is minus 1. So if I want to know the y coordinate, I put it in the original function. So this is, if you want, I can write it up there. It is f of 1. Is a local minimum. And now I calculate f double prime of the second number, 1/3. So this becomes 6 times 1/3 minus 4. So this definitely becomes negative. So this means that 1/3, okay, I'm lazy to calculate that. Let me just write 1/3. F of 1/3 is a local maximum. So I would say that we were lucky because both of them worked actually here. None of them become 0. And then I hope that you agree with me, if it works, it is faster in this case. Yes, because if you wanted to do using the first derivative test, after this step, of course, you didn't need the second, of course, but here you need to draw that table. But here, if it works, but of course, if you have a fraction function, calculating the first derivative is already hard because you have to use the quotient rule, and then calculating the second derivative becomes even harder because then you have a more involved fraction. So, I mean, theoretically, you need to know about this theorem, but which one you want to use, it depends on the nature of the problem which is given. Is that clear? Okay, I would say that let me stop here. One small part of these 2 pages, these 2 sessions I have just covered 1.5 page in the book, okay? So that is called optimization. That is also a very important one. Then I will teach you that when we can go faster. Yes? But mainly I wanted to review these things because I didn't know how much you learned about these things or how much do you remember from last year. Okay, any questions? Okay, so more or less the same number, the same pages you have to study in the book and the same exercises. We haven't progressed. Thank you.